makes me dizzy. Okay. I just forgot that there's no school in Stapleton, but I've connected to Stapleton anyway. So I guess we can hang up in Stapleton. Okay. So anyway, let's see, what we need to do is we need to check out our sources here, PC output. Okay, so we're showing our PC, that's great. Okay, so looking at our schedule here. Now I don't think I've posted this yet to Blackboard. I don't think I've emailed it out to everybody yet, but we changed the schedule slightly so that we had a couple extra days on our bridge project, and now it's the 23rd of September, so we're here on chapter 5.1. And then we'll have homework, chapter 5, problems 2 and problems 4. And we'll also cover chapter 5.2 and 5.3 over the next couple days. We'll see how long it takes us to get through this stuff. We've got quite a bit of material to cover, but the homework problems at the end of chapter 5 sound like this. The first one is to pick one of the following household items and list as many creative uses as possible. Coat hanger, spoon, toothpick, piece of paper. And then number 4 says, how could you keep raindrops from blocking the view through a windshield without using squeaky windshield wipers? List 5 ideas. So these are 2 problems that involve what we call the engineering design method, particularly the first couple of steps of the engineering design method. And the further on that we get into this class, the more of this method we'll be using. So we're getting started on it here. There are other problems in this section that are really good ones. Design a system that places radioactive tennis balls in a safe bucket without human touch. We're actually going to do something like that later on in the class with our hydraulic arm project. We'll be designing a system that communicates across the room. We'll be designing something that moves something with the motor project. We'll be doing the trebuchet project to throw something. So we'll be doing lots of different projects that involve the design process. But the homework for now is just the beginning of the design process. So we've already seen kind of the basics of the design the design method, the engineering design method. We've talked about it before. We've searched online for different versions of the design method. And I'm going to go ahead and switch over to my overhead camera so we can see what we've got going on here. So let's see if I can switch my output to my overhead camera now. Input to my overhead camera. Maybe. Maybe not. Okay. See if we can get this to focus in and zoom in a little bit. So this is on page 119 in your textbook. This is what we call the engineering design process, and like I said, we've seen this before a little bit. There we go. Excuse me. There are 5 different sections of this. There is the synthesis section, and then synthesis and analysis section, communication section, implementation section, and the analysis section in this particular version of the design cycle, which we're going to use in this book. There are lots of different types of the design cycle, but all of them include essentially these 5 elements. Just maybe they name them something differently. Maybe they break them down into different sections. Notice that here in the synthesis section, we have 1, 2, 3, 4 subsections. In the synthesis and analysis section, we have 2 subsections. And notice that there are arrows pointing through this. There are arrows that you start at number 1 up here at the top, identify the need and define the problem. And then you can go down to assemble the design team, and down, down, down. And then you can go down here through feasibility study, But then you can go down these directions, but then you can also go back up through a loop. You can go back to the top and you can start over, and you can start over and identify the need and the problem. You can start going around in loops and loops as you're trying to figure out what you're designing. And so every method has these elements where you have different sections of the design process, and also this looping idea that allows you to go back into the design process and start over or do something again. And I want to take you now back to my computer, actually. So let's go back to source. And let's take a look at so let's take a look at the internet really quick and see what we've got as far as different design processes online. There's a lot of them. Let's see if I can find it here. That's not right. I'm about to look for Google. Where's my Google? I don't have Google. Here's a Google search. So So if we put in the engineering design method or an engineering design process, you can see a lot of different things come up, a lot of different processes. Let's take a look at this one. This one's fairly small, so let me zoom in a little bit here. Whoops, not too much, can't read it. Okay, so this one is specific to civil engineering and also specific to a specific type of civil engineering, where they're designing a pier for a bridge. In other words, one of these big footings for the bridge. So they're selecting a bridge pier, calculation of variation and ductility, and they go through this process, and there's two different things that have to be done, and that gets you through, right? Let's look at let's look at a different one that looks completely different. So in this one we have the phases of design here, and up at the top I can't really read that. Goodness, what is going on here at the top? Can't read what it says there, but you've got this these loops here that are considered the cycles or the things that you have to go through again and again and again to get things right. And here they start off with a concept, and then they go to a model, and they go to a prototype and a mature design, conceptual design, preliminary design, design detail, production development, and so on and so forth. Notice that there's always this loop factor, but you do step through step by step. Just a different way of representing a design loop or a design method. There's another way of representing it. Try to get this zoomed out a little bit. So here we have different types, different parts of the design, and you're gonna, let's see, what is this one talking about here? I can't figure out what this one's talking about. Let's actually not do that one, since I can't figure out what specific field that one's supposed to be in. So here's another one that's kind of interesting. In this one, you recognize a need, and then you go down into the cycle. So we start up here, recognize the need, we analyze the need, we set objectives, we create alternatives, we set target specifications, we screen for feasibility, develop alternatives, select alternative, evaluate the probability, and if If the probability is good, we go ahead and communicate the solution. If it's not, we go back to analyzing the need and setting objectives and so on and so forth. You can go around and around this thing until you find a solution that works, that's going to be succeed, and then you communicate that solution, right? What is the purpose of these things? Well, there are literally hundreds and hundreds of different design loops, design methods for engineering. What is the purpose? Well, here's one that will actually kind of show us the purpose. The purpose is to imagine some kind of solution to a question. So we ask a question. How do we deliver a package to a customer? How do we turn on a turn signal in a car? Whatever question you have, there's some kind of problem in the world that needs to be solved, some kind of question that needs to be answered. We come up with a solution by using our imaginations, and maybe we come up with hundreds of solutions, possible solutions, you could call them. And we make a plan to implement one of these solutions, then we create something that actually is one of those solutions. We experiment on that to see if it works. If it doesn't, we improve it. If it does, maybe even then we improve it. And then we ask another question, and we keep going around this cycle. We keep inventing things, we keep developing things, we keep improving things, and we make the world into what it is. Okay? So, all of this stuff, however, needs to be centered around the goal that we're trying to accomplish. And that goal comes from asking a question, having some kind of problem, imagining and planning a solution. Right? We get to that goal by going through this process. The goal being to solve a problem of some kind. Right? And you can go through it, you can explain it in several different ways, you can represent it in hundreds of different ways, but in the end goal is the same. We want to develop solutions to problems. Here's another one that's a good one. This one's a little bit more detailed, but we define the problem in step one. We research the problem. We brainstorm possible solutions. We choose the best solution. We build a model or a prototype. We test the solution. We test our model or prototype. And then we improve it somewhere in here. We communicate what we've done. We redesign if we need to improve it. We redefine the problem if we need to, and we keep going around this cycle. Eventually, something's going to get kicked out of this cycle. Eventually, some kind of product or some kind of solution or some kind of whatever. We're going to put it into a factory and make it and sell it, or we're going to put it onto a space shuttle and launch it into space, or we're going to do whatever we're going to do with it. But then there's always going to be a new problem, and we're going to keep going around and around this loop. And that is the idea of all of these types of things. We're always looking to ask a question, solve a problem, or look for solutions to a problem, and go through this process to get the problem completely or truly solved. Since you can't ever completely or truly solve the problem, we're always going to have things to go back and do. We're always going to have new cycles to go through and everything else. So what we have done in this book here is we have broken this into 5 different sections. The synthesis section, which is where we're going to come up with ideas and solidify those ideas into some kind of a design. We're going to analyze designs, and we're going to choose the best one. We're going to write things down. We're going to communicate things to people that need to know. We're going to communicate with others that can help us. And then we're going to implement this process. We're going to make a prototype. We're going to make a model of some kind. And then we're going to figure out if that model is working. We're going to figure out if our design is a good design. And if it is, then maybe we put it into production. Maybe we improve it. Maybe we do whatever we do with it. Or if it's not, maybe we go back and fix it and make it a better solution. Or we start all over again and find a new solution. We can go back. Here this arrow shows us going back to the beginning, but really we can go back to any point in this and fix what needs to be fixed. The rest of chapter 5 essentially just steps through these processes a little bit at a time. Okay? The end result is to be a successful engineer. Here are some successful examples of successful engineering, right? People who have built there's many, of course, many planes and cars, and that's what they're showing on this page. So we have a guy that built a human-powered plane. So here is a human-powered plane. It's essentially like a bicycle in the air. And he won a prize in 1977 for doing that. In 1981, we have a solar-powered aircraft that was designed. Here we have a solar-powered car, an electric car, right? The first electric car that was made by General Motors. And there's lots of other examples. These are just 4 examples that I think are actually chosen for political reasons, but call me crazy. But they're good examples of people that successfully navigated the engineering design method or used the engineering design method to create something, right? However, the first step is to define the problem. Identify a need and define a problem. How do we do that? Do these things here, do they define a problem or identify a need? Well, I would say probably no. At least in 2 of these cases. We don't really have a need for human-powered flight. There's no problem to be solved there necessarily, except that, if you want to have human-powered flight, you need to have a plane that's very light and very efficient, I suppose. Solar-powered flight, maybe there's a need for that. That's a good thing, but anybody who knows anything about solar power realizes it's not going to happen because there's just not enough energy that we can harvest. Solar-powered cars, electric cars. Certainly with those 2, we have a problem and a need. What is the problem? The problem is pollution from gasoline, and the need is that we want to have cars that are more efficient and don't use up so much gasoline because gasoline is getting expensive. Well, the problem with either of these 2 cars is that neither of them met that need. And so while the engineering method was followed after the beginning, at the beginning they didn't really realize what the problem was. The problem is not that people want to drive cars that don't burn gas. The problem is people want to drive cars that cost them less money, and people want to drive cars that are reliable, and people want to drive cars that are clean. That's probably the 3rd thing they want to do. They'd much rather drive a cheap car and a reliable car than a car that's clean. And so these 2 cars didn't meet those criteria because they were both so expensive they had to stop thinking about them at all. Not just stop making them, they stopped thinking about them. And the electric car that GM Motors makes now is no different. The one that they make right now is the Chevy Volt, and you can only afford to drive it if you're a millionaire, essentially, because fixing it costs as much as buying it. The Prius is very much the same way. The only people that buy Priuses and that afford Priuses are people that make a lot of money. So it's not a very good solution to the problem that we have. The people that want to save money can't afford to buy the car. And the people that buy the car don't need to save the money. So it doesn't make any sense. But again, this is the idea of politics getting in the way of engineering. What kind of car really does solve the problem of needing a cheaper car and having a cleaner car? Well, a car that runs on clean diesel. A clean diesel car puts out much less carbon dioxide, much less carbon monoxide, runs very cleanly, very efficiently, and very cheaply. But people don't want a diesel car. They think diesel cars are loud and dirty, and so the public's perception of diesel needs to change. So again, with engineering, it's not necessarily just straightforward stuff. We do have to deal with politics, we have to deal with public opinion, we have to deal with lots of other things. So oftentimes the problem that we're dealing with is not just an engineering problem. You have to think in terms of who you're selling this to. You have to think in terms of what does the government think of this. You have to think in bigger terms sometimes, more social terms than just engineering terms. So, in other words, we have to be human, and we have to realize there's always a human factor. But how do you define a problem? This is the first step, to define the problem, right up here. Identify the need and define the problem. How do you define the problem in engineering? I don't like this design method because in this design method they say assemble a team, a design team, after they say define the problem. And sometimes you need a team to define the problem because really what defining a problem requires is lots of talk and communication and kind of brainstorming and some arguing maybe. And you need a lot of minds to do this. It doesn't always, one person can't always define a problem very well because their own personal prejudices, their own personal experiences often disqualify them from the ability to define the problem. So I'm going to say that to define a problem, you need to get your team together first. You need to know basically what the problem is so you know who to choose for your team. If your problem involves electricity, you're going to have an electrical technician involved or some kind of electrical engineer involved. Somebody that you think is close to the problem will understand the problem. And sometimes that takes a lot of understanding. You have to know the people that you're trying to get to work for you. You have to understand the problem to some depth. You have to understand people in general. You have to know a lot of people so that you have a big group of people to choose from. Sometimes you don't have a choice. Sometimes you have a team to work with and you just got to work with them. So to define your problem, you're going to want to sit down, get a lot of paper, get some computers, start writing things down, start sketching things out, and define what it is you're trying to, your goals you're trying to meet, the problem you're trying to solve, the question you're trying to answer. Really, without examples, it's difficult to talk about how to define this problem. However, it can be done. So, let's talk about assembling a design team just for a minute. Assembling a design team is going to require probably at least 2 or 3 people, otherwise it's not a team, right? And you're going to want some kind of leadership. Somebody's going to have to be in charge overall, and that can be one person or it can be 2 people maybe, but usually not more than that. And everybody's going to want to have defined responsibilities on the team. Some people may be your engineers that are in charge of design. Some people are going to be your engineers in charge of prototyping. Maybe somebody who's going to be in charge of all the electrical systems, and somebody's going to be in charge of the heating systems. Somebody's going to be in charge of the flight controls in an airplane or whatever. But you're going to have defined responsibilities. So you've got to make sure that you define responsibilities for each member. And there's going to have to be some kind of leadership structure. Okay? So if people need to report to other people, that needs to be defined and set forth right away. So building a team is a whole subject in and of itself, but it needs to be done properly. It needs to be done in an organized manner. You need to know how you're going to communicate. You need to know how you're going to keep track of things, how you're going to keep records. Maybe who's going to keep records, who's going to be in charge of money, who's going to be in charge of talking to the bosses, whatever. There are just thousands of things that you could have involved in that, but with simpler teams it might not be so much. But those things should be in place. Your team should be organized, and it should be formed completely. Then, step 3 is a biggie, and this starts on page 22. Identifying constraints and criteria for success. They have 1, 2, 3, 4, 5, 6, 7, 8 bullet points to start with, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bullet points to follow up. And we're going to go through these one at a time, and then we'll be done with, well, we won't be done quite with section 5.1. We have one other one. There are a couple other sections. Anyway, we're going to go through these today. So, we're going to go through them as quickly as possible. Budget. The first one is budget. Let's zoom in here so we can kind of see what I'm pointing at. This is page 122. Where's my Zoom? Here's my Zoom. So the first thing that they talk about here is the budget, right? Most projects are going to have some amount of money that you're allowed to spend, at the very least. But other projects may have a very complex budget, where you're allowed to spend this amount of money and this amount of time on this kind of thing, and other things have different kinds of money. That needs to be organized. You need to know what that is. Time. Time constraints are often placed on engineers. Okay? So you need to know what kind of time constraints you have. Do you have to have a report done by a certain time? Do you have to have a project done by a certain time? Do you have to have a prototype ready by a certain time? Do you have to have tests done? Are there different times for different things? You need to know that, and you need to keep track of it. Personnel. Okay, you need to know everything about the people on your team and anybody that they have to work with as well. Legal issues. Oftentimes you have to deal with legal issues. Sometimes it has to do with just what you're doing in general, but sometimes it has to do with very specific things inside your team. Maybe you're working with special chemicals or special devices that require particular handling or require that you have particular paperwork to use them. So many different things are involved with the legal aspects of engineering. You can't just throw things away or pour things down the drain. Sometimes you have to have special permits and do things specific ways. Material properties and availability. When you're working with materials as an engineer, you're going to have to keep track of them. Sometimes you're going to have to keep track of how much you use. Sometimes you're going to have to keep track of how you use them. Sometimes you're going to have to keep track of them because they're dangerous. Material safety data sheets are something that you have to keep as an engineer. So sometimes you're going to have to keep track of what materials are going to be available for your project. Maybe you're all ready to build a submarine, but you don't have enough titanium for the part of the hull because that titanium hasn't been mined yet. So you need to be aware of those things. Off-the-shelf construction, right? Sometimes you're allowed to use stuff that has already been designed for something else. Maybe some company has designed a computer that you can use in your submarine, but maybe the Navy does not want anything from some other company in their submarine because they have whatever, right? They have some kind of security constraints or whatever. So you need to know whether or not you're allowed to use stuff that's already been designed maybe by somebody else. And if you're not, then you need to plan for that because it's going to take you longer if you can't, most likely. You need to know what kind of competition you have. Why do you need to know what kind of competition you have? Because you need to know how fast they're working so that if you're competing with them, you can get done quickly. You need to know maybe what they're doing so that you're not doing the same thing. Two companies doing the same thing is usually not a good thing. Manufacturability. You need to be aware of if something can be built. Sometimes it's very easy to make a prototype of something, but very difficult to put it in a factory and make it mass produced. So you have to know about that. You have to understand something about welding, about machining, about woodworking maybe, or plastic working, or molding things. Whatever it is that you might need to know to produce the product, you need to understand about it so that you can know if it can be made. Or you need to have somebody on your team who does. Or you need to go to somebody who does. Now this is a lot of stuff to start with. These are things for you to think about, but you don't need to necessarily memorize them or remember them right now. As you move forward in engineering, you will learn these things again and again. But those things are absolutely necessary as you're putting your team together and as you're working on this project. Because these things are going to help you to figure out what are the overall constraints of the project? What's going to hold us back? What's going to guide us in a particular way? All of that kind of stuff. What do we have to do? What are the things that we have to stay within? It's kind of like the rules for working on your project. Once you've done that, then you need to start listing off the things that are going to make this project work. They're going to make it successful. And there's lots of different things you have to think about when you're listing off the things that are going to make it successful. Aesthetics. Okay? Sometimes look is really important. In fact, often the look of something is very important, how it looks. I'll give you a couple of examples. In the cycling world, cycling is one of the most engineered sports there is, as far as engineered sports that are not mechanical, or not motorized, right? So human-powered sports, cycling is a very, very engineered sport. There's a lot of engineering going in there. New devices in cycling do not have a chance of surviving if they don't look great. Several years ago, they built a great device for automatic shifting on a bicycle, but it was just big and clunky and ugly, and it died. Just a couple of years ago, a company developed a new system, which was essentially just the old system with new batteries and a new look. And now, it's a hot item because it looks great. Okay, cyclists and many other people really care about how they look. Another good example of that is in tennis. There are all kinds of tennis rackets out there, but it's not necessarily the best tennis racket that everybody uses. It's the one that looks the best. Okay? Performance. Of course, how something performs is important. Absolutely, it's important. The quality. Of course, the quality is important. These aren't in any particular order, but the more important ones are towards the front here. Human factors. Right? It must be ergonomic, easy to use, easy to understand. It must meld well with the human body if it's going to be used by the human body, right? So on and so forth. Cost. Right? Cost is important. First of all, how much is it going to cost to start this project and to get it underway? Because sometimes some projects are really difficult to come to start, but not so hard to keep going. But the life cycle cost is also important. If a product is not hard to get started, but it takes a lot of maintenance to keep it going, that's something you have to think about as well. Safety. You always have to think about safety. Operating environment. Interface with other systems, with other products. Effect on the surroundings. Logistics, right? There's oftentimes your product, the thing you're designing, is just part of a bigger system, and it has to work well with everything else. That's logistics. Reliability, often important. Reliability, right? Maintainability, preventative maintenance, serviceability, and availability, right? You need to address each one of these things with your team once you put your team together and you figured out what the problem is, what is the problem you're trying to solve. Then you go through and you talk about each one of these things, how important they are to you, maybe rank them in order of importance, and talk about how you're going to achieve these things in kind of a general way. What your product is going to do to achieve good logistics, good reliability, and so on and so forth. And start to flesh this thing out. Start to make put together some ideas on how reliable you want it to be, how maintainable you want it to be, how you want it to operate in specific environments. Once you have decided that, you've essentially listed all the things you want your solution to do. And once you've got a list of all the things you want your solution to do, then you can start to figure out what your solution is going to look like, or what it's going to be like. And that's when you start to search for solutions, which is step 4 of the process. And that is on page 124. Okay, so when you're starting to look for solutions, there's lots of different ways you can do this. And they've given us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bullet points. Okay, lots of different ways to go about this. Now, you can use a few of these different ideas, you can use one of these ideas, you can use all of these ideas, you can use more than these ideas. But essentially, what you're trying to do at this point is you're trying to find possible solutions. You're trying to come up with as many things as you can to to solve your problem, okay? So let's take a look at these different things we can think about as we're doing this. This will eventually lead to some brainstorming, okay? This will eventually lead to a brainstorming session where you're brainstorming ideas of problem solvers, ideas for your solution or ideas for your design. So one of the things is that they say is, can you eliminate the need, right? Can I eliminate the needs? Maybe you're trying to solve a problem, and maybe your solution is to just get rid of that particular problem, right? But maybe you're actually trying to solve a problem, and you're going to go think outside the box, right? They challenge basic assumptions. And thinking outside the box is important. Number three of the things that's important to do during this process, which is right here, is to be knowledgeable. To be knowledgeable, you have to understand things, you have to learn things constantly. So you have to be reading a lot, you have to keep up on engineering. Also, you have to be able to employ analogies. So you can liken one thing to something else that is completely different, but similar in some ways. For example, you can liken voltage to flow of fluid through pipes, or something similar, right? Be able to personalize the problem. You're actually able to see things better if you can make it something that's like in your life, right? So try to personalize problems. Identifying critical parameters. You need to know what is absolutely necessary in the project, or absolutely necessary in the problem you're trying to solve. Oftentimes, you're going to switch functions of something. So, for example, you've got an object that is designed to pull packaging out of a box or something like this, and maybe it works really well for that, but maybe you're going to be able to use that device that pulls the packaging out of the box to do something else, or maybe to do two things at once instead of just pulling the packaging out. So you've often got to work with what you've already got and see if you can come up with a new idea for how to use it, right? Alter sequence of steps. Oftentimes in engineering processes, you have things that happen in a particular order, and sometimes you can solve a problem or answer a question, or create a solution just by changing things around, changing the order you do things in. And maybe you can reverse things, right? So reversing the problem. Repeat components of process steps. Sometimes you just got to do things twice or three times to make it work, make the problem go away. Sometimes you're going to have to separate functions out or combine functions. And sometimes you're going to have to just start from scratch and say, what am I trying to do here? This is the use vision part, right? And always, through all of these things, you're going to have to employ basic engineering principles. So thinking of all these things that you got to do when you're trying to come up with solutions, all these things we just mentioned, these 13 or 14, whatever they were, now you're going to go into the brainstorming session. This is addressed on page 127. Now, normally I would have everybody go through a brainstorming session as part of an assignment. But I'm not going to do that in this particular class because we have students kind of spread out in ones and twos everywhere. You can have a brainstorming session with 2 people, but it's much easier with 3 or 4. We will not do that because it's much better live and in person. But brainstorming should be a group of people, and they have the rules, not the rules for this, but kind of the guidelines for this, on page 127 here. Should be a group of people, 6 to 12 people. There should be a fair amount. And you have to have a leader that is going to allow free expression. In other words, the leader's just going to say, we're going to brainstorm about this particular thing, go. And he's not going to stop people from sharing ideas. He's not going to say that's a dumb idea. The only thing that he might do is steer people back on topic if they stray too far off the path. Right? The best kind of leader for that is one that sits down and says, we're going to brainstorm. All ideas are welcome. We need to keep track of these ideas somehow. Maybe you record the session somehow, or somebody takes notes, or everybody takes notes. And we're going to open it up to all ideas. We don't care how crazy they get. We don't care how outlandish they get. We're just going to open it up to any ideas that we think might solve this problem. And then group members have to be willing to open up and to share their ideas no matter how crazy they sound. Because one crazy idea may spark another crazy idea, which might spark a not so crazy idea that really works. I can give you an example of this. I had a person from the community come into my office the other day who had this great idea that he wanted to develop into a product that he could sell to Cabela's. So we sat down and we started coming up with ideas, just brainstorming, just different ideas, this crazy thing, that crazy thing. Eventually we came up with essentially the same thing he came in with, was the best point, was the best design, but we also came up with some other things we could add to it that were certainly not crazy, but they started with kind of going off in a crazy direction. I'll give you details, but I'm not supposed to share, his idea with other people. In the end, we included one other person in this idea, and he came up with a few crazy ideas, but one other great idea that I think is going to make this product really powerful. So now this guy has a product that I think can easily sell and maybe even make him millions in the end. Okay? Just by throwing around a bunch of crazy ideas and bouncing them off each other. Okay? You need to be open and free with this. But if you're starting off with an idea on how to make a wheel turn faster on a car, and then you end up talking about birds and birdhouses, you need somebody to guide you back. So there needs to be a balance between those two. And there are different techniques. They show here the nominal group technique and the Delphi technique. There's lots of different ways to go about this, but in the end, it's mostly just about free expression. The last two parts, or the last four parts, I guess, or a few parts, I don't know how many there are, of section 5.1 talk about the feasibility study, where you're going to take all these ideas that you came up with in your brainstorming session, and you're going to kind of study them. You're going to maybe give every group member a few of them to go out and study, and you're going to try to decide whether or not you can do this. You're going to look at what is going to possibly be necessary in each idea, what kind of design, what kind of materials, just basically, not going into great detail, and decide which ones are the most likely candidates for a good design. You're going to try to whittle it down to the best designs that can be actually accomplished without too much money, that will solve the problem, and so on and so forth. And you want to have a balance between cost and design effectiveness. And cost, not just in money, but in time and resources and people and everything else. And you're going to choose from this overall study, you're going to choose the best designs, maybe as many as 5 designs, but usually, just a couple. And then you're going to start to document those solutions. You're going to start to write down things, make drawings. You're going to come up with the materials that you might need, just to try to give some more detail to these designs. And then once you've got it down to just a few designs, then you're going to take those to your bosses or to whoever, and they're going to review those, and we're going to work on choosing the best design in the end. In 5.1.6, they talk about preliminary design, where you go through and you start to make drawings, maybe you start to calculate costs, you start to put materials into the equation, maybe you make computer models, and then you can actually whittle it down to maybe the best design, the best solution. Once you've got it down to one solution, that's when you actually start the real design process. You start making real detailed drawings, you start laying out specifications, you start looking at materials, you start looking at people who build parts that you might use, so on and so forth, and all this. And once you've gotten through that, you're actually going to start building your solution in a prototype or a model and testing it to see if it works. Right? So that is the basic idea of the design process and how you go through that. And we're going to see some examples of this in our next couple of lectures. We're going to go through quite a few examples of this in our next couple of lectures. So on Wednesday, we'll go through some examples of products that use the design process. We'll go through step by step. And then on Friday, we'll finish up. And next week, we'll start our new project, which will be the slow-moving car project. All right, so I think that's everything we've got for today. We'll go ahead and end there. Have a good day.